Good morning, all of you. And we shall continue the system classification. We have completed static system, dynamic system, causal, non-causal, and linear and non-linear system, time invariant and time variant system. Okay. So next classification, stable and unstable system. Stable and unstable system. So the definition for stable system, a system is said to be a stable system for the bounded input signal. The system should give bounded output. Okay. Otherwise, it is called as BIBO stability, BIBO stability criteria. First, let us understand what do you mean by bounded input. Example, bounded input signal. Bounded input signal meaning the magnitude of the signal is always a finite value. The amplitude of the signal is finite for all the values of t, from minus infinite to plus infinite. At any instant of time, the amplitude of the signal is finite. Okay? So then that signal is said to be a bounded signal. Example, any DC signal, a constant value of 1 or 2, okay? It's a bounded signal. Or sine t, or cos t, or u of t. So these are all some of the example for bounded signal. Okay? Because if you look at the sketch for a constant DC, t x of t, suppose the magnitude of the signal is 2. This is the representation of a DC signal with the amplitude of 2. So the amplitude of the signal is bounded in all the time instant. Okay. Or if we plot the sine t versus t, your amplitude of the signal for this particular signal 1 to minus 1, magnitude 1 to minus 1. So the amplitude of the signal is bounded. Okay. So likewise cos t, u of t. So these are the signal example for the bounded signals. Unbounded signal represent the magnitude of the signal is not a finite value from t minus infinite to infinite. Say for example, so we draw on ramp signal 0 t x of t, some signal. At t equal to infinite, the magnitude of the signal is infinite. Or we can give an example for increasing exponential, like this, and so on. Or real increasing exponential. So these are the signal example for a unbounded signal. Okay, the amplitude of the signal is not finite in all the time instant. The signal amplitude is finite all the time instant from minus infinite to infinite. Then the signal is said to be a bounded input signal. Okay. So what do you mean by stability of the system? For a bounded input signal, the system should generate a bounded output signal. Okay. This is the definition for stable system. For unstable system, even though if you are applying bounded input signal, if the system output is unbounded, then it is said to be unstable system. Okay. We'll solve some problem. Example, identify whether the following systems are stable system or unstable system. Y of t equal to x square of t. Y of t equal to x square of t. So usually to check whether the system is stable or unstable, we need to assume the input signal x of t is a bounded signal. You may assume any signal, u of t, sin t, or cos t, or a DC value, even for del of t. Okay, any bounded signal you can assume and check your y of t. If your y of t signal amplitude is also bounded, then the system is said to be a stable system. Okay. So most of the problem by substituting u of t, we will come to know. So u of t is a bounded signal. Look at the sketch for u of t. It has a magnitude of 1, from 0 to infinite. From minus infinite to 0, the magnitude is 0. So we may use this u of t as a test signal in most of the cases to check the stability of the system. Okay. So let assume the input to the system is u of t. So what do you mean by y of t equal to x square of t? X of t is the input to the system. X of t is the input to the system. The output of the system is y of t. So y of t is equal to x square of t. Let assume the input signal is bounded signal. We are applying bounded input signal. So obviously your y of t equal to u square of t. So u of t, the magnitude is 1 only. So even though if you substitute u square of t, the magnitude of the signal is 1. So that will be u of t. Okay, u of t signal 0 to infinite, a constant magnitude of 1, minus infinite to 0, a constant magnitude of 0. Therefore, it is a bounded output. For a bounded input signal, the output also bounded. Bounded output signal. Therefore, the system is stable system. Therefore, the system is stable system. Second example, y of t equal to integration minus infinite to t x of tau into d tau. Y of t equal to integration minus infinite to t x of tau into d tau. Check whether the system is stable system or unstable system. Assume the input signal x of t. So here the integration limit is t, so they are using the variable tau. Okay. Assume the x of t is bounded input. Assume the x of t is bounded input signal, a constant or a sine t. In this example, if you assume your x of t equal to sine t or cos t, then you will get bounded output only. But when you assume x of t equal to u of t, let us assume x of t equal to u of t. So integration u of tau into d tau. Integration u of tau into d tau. Do you remember the relationship between u of t and r of t signal? Integration of u of t d tau is nothing but r of t. Okay. So when we assume x of t, the input signal is a bounded input signal. So according to the system behavior, so we are getting y of t equal to r of t. Okay. So if we plot r of t versus r of t, the signal sketch will go like this. This is an unbounded signal. This is an unbounded signal. For a bounded input signal, the system generates unbounded output signal. Therefore, the system is unstable system. Therefore, the system is unstable system. Okay. Next problem. Y of t equal to t times of x of t. Now, how to check stability of this particular system? Okay. So, what is stable system? A system should give bounded output for the bounded input signal. What are the bounded input signal? You may give a constant input, or you may give a cos t, or sin t, or u of t. These are all bounded input signal. So in this example, if I assume my x of t is a constant input, I'll tell you why I'm checking this. X of t is a DC value or a constant input. That is x of t equal to 1. Now my y of t equal to t. So y of t equal to t is what? Y of t equal to t. That is your r of t function. What is the function for r of t? R of t equal to t for t is greater than 0, 0 otherwise. Okay. So in this example, y of t equal to t times of x of t. If I assume my bounded input signal x of t is a constant DC, a constant DC value of 1, that is x of t, t versus x of t, I am assuming my input signal is a constant, a DC value 1. Now my expression y of t equal to t. How to plot your y of t versus y of t equal to t, t versus y of t. T0, 0, T1, 1, T2, magnitude 2. So it will go like this. It is an unbounded signal. For a bounded input signal, the system gives unbounded output signal. Okay. Therefore, the system is unstable system. Therefore, the system is unstable system. Okay. So in this way, you have to logically check the given y of t expressions. For some particular bounded input signal, the system may give a bounded output signal. Okay, then we cannot come to the conclusion. So in this example, if I assume x of t is a constant, a bounded input signal, now my y of t equal to unbounded output signal. Therefore, the system is unstable system. Okay. So problem number 4. Suppose y of t equal to e power x of t. Y of t equal to e power x of t. Comment on its stability or identify whether the system is stable system or unstable system. So let assume x of t is a bounded input. X of t is a bounded input. Any value you are assuming. So are generally the x of t between minus b to b. B is a constant. You can assume any value for this x of t, a bounded signal. So your y of t between e power minus b to e power plus b. Assume x of t equal to 1 or x of t equal to 2 times of u of t. So whatever bounded value you can assume for this particular x of t. So for all the input of your x of t, your result would be y of t between e power minus any constant up to e power plus constant. Okay. The output never enter into infinite, or the amplitude of your y of t will never infinite from minus infinite to t. For all the values of t, your y of t is always finite. The magnitude of your y of t is always finite value. So therefore, the system is stable system. For a bounded input signal, if you are assuming unbounded input signal, then that will be different. For a bounded input signal x of t, whatever input you assume, your y of t lies between e power some constant minus to e power plus some constant. Okay. So these are all some example for continuous time system. Okay. Now we'll go for discrete time. Y of n equal to x of n plus x of n plus 2. Y of n equal to x of n plus x of n plus 2. Can anyone tell now whether this system is stable system or unstable system? Stable system meaning for a bounded input signal, the system output should be a bounded output. Should be a bounded output signal. Y of n equal to x of n plus x of n plus 2. Can you tell me whether it is stable system or unstable system?
Unstable, sir.
How it is unstable? Let us assume yeah, x of n is a bounded input signal. Most of the cases we are assuming or we are considering x of n equal to un as a bounded signal. So y of n equal to u of n plus u of n plus 2. Whether your magnitude of the signal enter into infinite? In this case, what is u of n magnitude? What is u of n magnitude of the signal? 0, 1, 2, 3, 4, 5, and so on. The magnitude of the signal is
1.
1. So e of n plus 2, we substitute e of n plus 2, that is 0,
Minus 2 means 1, sir.
starting from minus 2 onwards, 1, 2, and so on. So if we add these two signal magnitude, so will you get any infinite value?
No, sir.
Oh, for a bounded input signal, your output signal y of n amplitude is also a finite value for all the values of time between minus infinite to infinite. For all the time instant, your output signal magnitude is bounded. Okay, therefore, output of the system is bounded. Therefore, the system is stable system. Therefore, the system is stable system. Okay. The last one. Y of n equal to 1 by x of n. Y of n equal to 1 by x of n. Now we have to comment about the stability of the system. Okay. Stable system represents for any bounded input signal, not a particular bounded input signal. Okay, they have to check all possible bounded input signal. The system should give a bounded output signal. So then only the system is stable system. So we are solving a problem. Most of the cases we are assuming x of t equal to ut. Or some cases we can logically check t times of x of t. If we assume x of t equal to a constant input 1, then y of t is equal to t. So it's an unstable system. Okay. Here, if we assume any value for x of t, a bounded input signal, the output may lies between e power minus some value to e power plus some value. Anyway, it is a finite magnitude it at all the time instant. Therefore, the system is stable system. And fifth, also we are assuming x of n equal to un. Then while analyzing this un plus u of n plus 2, the amplitude of the signal is always finite at each and every time instant. So in this example, y of n equal to 1 by x of n. If x of n is 0, if x of n is 0, what is the value for y of n?
Infinite.
Okay. So x of n is a bounded signal. This may be a simple DC value or a sine function or a cos function or a unit step function. Okay. So if you go for sine function, the possible values for the magnitude sine function minus 1 to 1. Okay. Or in this kind of problem, by looking at the problem itself, we can easily identify y of n equal to 1 by x of n. If x of n equal to 0, your y of n, the magnitude of your signal would be infinite. So this is a bounded signal. This is an unbounded output. Okay. So these kind of problems you have to check logically. Therefore, it
సార్
is.
ఎక్స్ ఆఫ్ అని 1 తీసుకుంటే 1 కదా సార్ వస్తుంది.
That's why we cannot restrict it to only one signal. We cannot restrict it to only one signal. You have to check for all possible cases. Okay. So this is some exceptional cases among all these problems. Okay. So remember that whenever you have the problem in this type, then you have to check for x of n equal to 0. Then if y of n is infinite, then it is an unbounded signal. So there is no fixed rule to check whether your system is stable or unstable. Out of all the classification of system, stability checking, there is no fixed rule. In general, it is a bounded input signal. But we cannot check for all the input x of t or x of n equal to a DC value or sine function or cos function or u of t value. It's very difficult. Okay. So in the second problem, y of t equal to integration x of tau d tau. If you assume x of t equal to sine t, then you will get a bounded output signal. But actually that is not true. Okay. So little bit difficult only for the students. You have to think logically and identify whether it is stable or unstable system. In unit 2 also we will be solving the stability checking for an LTI system. LTI system represent linear system as well as time invariant system. A system satisfy both linearity as well as time invariant property, then it is LTI system. Then we will be solving the stability of the system once again with the help of some other formulas. Okay. So you may expect LT system stability in unit 1 itself in the question paper, or like this simple y of t or y of n expression will be given to you. You have to identify whether the system is stable or unstable. Right. So one last problem with this, we will complete this particular topic. y of t equal to x of t plus 2. Can you tell me whether it is stable or unstable for a bounded input signal? Very simple notice. You no need to think much. There is no integration, differentiation. Just y of t equal to x of t plus 2. Whether stable or unstable.
Stable.
Yeah, stable system. Because for any bounded input signal, the system should give bounded output signal. So in this example, I am assuming my x of t is some constant, or x of t equal to 2 or something like that. A constant I am assuming, t versus x of t. I can keep from minus infinite to infinite. My amplitude of the signal is finite. So t2 plus 2, I'll get 4. From minus infinite to infinite, the y of t amplitude is finite. Therefore, this is stable system. So in general, please remember a stable system should give a bounded output signal for a bounded input signal. Okay. So last classifications of system. If we cover this particular topic, then unit 1 will be completed. Invertible and non-invertible system. Okay. Invertible and non-invertible system. So what do you mean by invertible and non-invertible system? First, we'll understand the concept and we'll go for the definition. A continuous time system or a discrete time system. Okay. First, let us assume a continuous time system. The system input is x of t. And the response of the system is y of t. Or the output of the system is y of t. Okay, now, this y of t, this system is invertible. If this particular system is invertible, if and only the inverse system exists. The inverse system exists for this particular system. What do you mean by inverse system? If I design a suitable system, I can able to get my x of t again. Then this particular system is said to be invertible system. For example, x of t is the input to the system. The system output y of t equal to 2 times of x of t. What is y of t? 2 times of x of t. Is it possible to design a inverse system such that to recover our x of t back, the output of the system is w of t, it should be equal to x of t. Is it possible? From 2x of t, I need x of t only. So if we design a system y of t equal to, so w of t equal to half of y of t. Is it possible now? W of t equal to half of y of t. What is y of t? 2 times of x of t. So these two will be cancelled, we will get x. Okay. So a system is said to be invertible system if the inverse system exists for this. Okay. Or a system is invertible then when an inverse system exists, that when cascaded with the original system yield an output W of t that should be equal to x of t to the first system. Okay. So this is the definition for invertible system. I'll write here. For an example, system output equal to 2 times of x of t. So I am designing a one more system. That system output is equal to 1 by 2 of whatever input we are applying at this step. So in this particular step, the input to the system is y of t. Y of t is input to this system. W of t is the output of the system. If I design W of t equal to 1 by 2 of y of t, then I can able to recover my x of t again. X of t is the actual input to this first system. So this is invertible system. This is the inverse system for this. Inverse system. So using the appropriate inverse system, is it possible to recover x of t that is input to the first system? Then this system is said to be invertible system. Okay, don't worry. While solving the problems, you can understand clearly. I'll write down the definition here. A system is said to be invertible if the input applied to the system can be recovered from the output of the system. Can be recovered from the output of the system. Okay. Simple definition. A system is said to be invertible if the input applied to the system, that is x of t, can be recovered from the output of the system. So for this particular system, from this y of t, is it possible to recover our x of t again? Okay. If it is possible to recover our x of t again from this y of t, then this system called as invertible system. A system is invertible, definitely your inverse system exists. Okay. So how to check whether the system is invertible or not? To test invertible or not. There are two steps. One is a system should not produce zero output, because if the system produces zero output, then we cannot guess what will be the input. If a system produces zero output, if cos pi by 2, what is the value of cos pi by 2?
0, sir.
0, sir.
In 0, 0. So we cannot guess whether it is sine function is the input or cos function is the input. So To check whether the system is invertible or not, the system should not produce a zero output. Okay, if the system produces zero output, then that system is non-invertible. Then that system is non-invertible. Because from zero information, we cannot guess what will be the what would be the actual input to the first system. Okay. Second one, distinct input to the system should generate distinct output. If a system gives same output for more than one input, same output for more than one input or different inputs, then that system non-invertible. Okay. First, we have to check these two conditions. If these two conditions are satisfied, then we try to find the inverse of the given system. Okay. Note, the output should not be zero. Very simple. If the output of the system is zero for a single input, for all input, the output should never zero for any of the input signal. Okay. Then first case. Second case, distinct input should produce a distinct output. Meaning, one particular input to the system should generate one unique output. If more than one input gives the same output, then we cannot able to identify the system. We cannot able to recover our original x of t. Say for example, sine pi 0, sine 2 pi also 0, sine 3 pi also 0. More than one input gives the same output. Or let us consider cos pi minus 1, cos 3 pi minus 1, 5 pi minus 1. So if more than one input gives same output, then we are unable to recover our original input. We cannot guess what would be the input, whether it is cos pi or cos 3 pi or cos 5 pi. So there are two rules to be satisfied. Output never should be zero for any of the input. And each and every input should generate a unique output. Or more than one input should not give the same output. These are the two rules to check whether the system is invertible or not. First example, identify whether the system is invertible or not. Y of t equal to cos x of t. Okay. Y of t equal to cos x of t. What is the rule? What are the two rules? Y of t never should be a zero value for any of the input. Okay. And also, if more than one inputs generate same output, then also the system is non-invertible. We cannot recover our x of t from the y of t information. So what is the meaning of this expression? A continuous time system accept a input signal x of t and the output of the system is equal to cost function of that particular x of t. So this is the actual meaning of this expressions. Now check the first two rules. X of t for x of t equal to pi. What is your y of t? Cos of pi minus 1. For x of t equal to 3 pi. What is y of t? Minus. So x of t equal to 5 pi, your y of t equal to minus. So we cannot identify because more than one input provides same output. So output is -1. From -1, how to identify my x of t? My x of t may be pi. My x of t may be 3 pi. My x of t may be 5 pi. So we cannot identify or extract our x of t by designing the inverse system. Okay. And in this example, two rules are not satisfied. So for x of t equal to pi by 2, y of t equal to 0. Okay. So what is the two rule for checking the invertibility? The output never enter to 0 for any of the input. And also more than one input should not give the same output. Because from this information, we cannot guess whether input is pi, 3 pi, 5 pi, 7 pi, and so on. And also pi by 2 equal to 0. Okay, output also enter to 0. Therefore, the system is non-invertible. The system is non-invertible. You have to write down the command. For more than one input, the system gives the same output. Okay. Therefore, the system is said to be non-invertible system. Second example, y of t equal to dx of t by dt. Y of t equal to dx of t by dt. Identify whether this system is invertible or not. A system, input to the system is x of t, output of the system y of t equal to differentiation of x of t by dt. So in this example, if we assume x of t is a constant value, x of t is a constant value, then y of t would become 0. So from 0 information, we cannot able to extract our x of t by designing any kind of inverse system. Okay. Therefore, the system output is 0. The system output is 0 for a constant input. For a constant input. Therefore, it is non-invertible. Therefore, it's a non-invertible. So one signal or one system I'll give you example for a invertible system. That is y of t equal to x of t minus 3. Okay. Y of t equal to x of t minus 3. X of t I'm applying to a system. My system output is y of t equal to x of t minus 3. Okay. So this system is an example for an invertible system. So if I design a appropriate inverse system, y of t, my output should be equal to x of t. So what should be the inverse system? From this y of t, I'm passing this y of t through the system. So I need to design an inverse system such that my y of w of t should be equal to x of t. So what value we can put here?
Y of t plus 3, yes, sir.
Y of
plus 3, sir.
t plus
3.
3, sir.
y of t plus 3. So if you replace, this is y of t equal to x of t minus 3. So if you replace y of t plus 3, wherever t is there, the t replaced by t plus 3. So 3 will be cancelled, get x of t. Yes. So y of t equal to x of t minus 3. So this is an example for a invertible system. Invertible system. If a system is invertible, definitely an inverse system exists for a particular system. So what is inverse system? We have to design or find the inverse system whose output is exactly equal to y of t. So in this example, if w of t equal to y of t plus 3, whatever in for this particular system, y of t is the input. So if the system function is y of t plus 3, then we will get w of t equal to x of t. So x of t is the actual input to the system one. So we can able to recover this x of t by designing a appropriate inverse system. Therefore, the system is invertible system.